I'm Zhang from Nanjing University. It's my great honor to introduce our work here today. Synchronized Behavior Checking, a new method for finding missed compiler optimizations. When one program satisfies certain semantic properties, the compiler can optimize the code to improve the performance. For example, if the if condition in one loop is a loop invariant, loop unswitching can move the conditional statement out of the loop, reducing branch jumps inside the loop and enabling other optimizations. However, sometimes although conditions meet, the compiler missed the optimization. This is called a missed optimization. In this example, size must evaluate to a positive number at line 7 in the first iteration of the loop. Otherwise, the loop condition will not be satisfied. Therefore, the true branch will be executed and the size remains unchanged in the first iteration, as well as all subsequent iterations of the loop. That is, both sides is a loop invariant. However, as shown in the compiled code, none of the optimization is applied by LLVM because it cannot infer both sides as a loop invariant. This is a missed optimization for LLVM. Missed optimization cause a waste of performance. How to effectively detect these missed optimizations is an important and continuous concern in recent years. Existing works design specific detection methods for specific optimizations such as data code elimination, arithmetic optimization, and optimization of data flow analysis. These approaches have shown good results, and some optimizations, such as data code elimination, can reflect problems with many compiler components. However, compiler optimizations are varied, and there is a lack of a general oracle to directly decide when a target optimization should be applied. We propose synchronized behavior checking (SBC) to address this challenge. The key insight behind SBC is that optimizations may not function in isolation. Quite the contrary, distinct optimizations often depend on related semantic constraints of the input program. This interrelationship induces coordinated behavior among optimizations, which can be utilized for cross-validation. In particular, for a target optimization, we look for other optimizations that have a related semantic constraints with it, detecting missed optimizations by observing whether their actual behavior is consistent with the expected coordinated behavior. Consider the program in this example. The applicability of loop switching depends on whether both sides is a loop invariant. Similarly, other optimizations may depend on the same semantic constraints, such as the elimination of the if statement at line 7 to 8 in the program on the right. The statement at line 8 will only be eliminated if the two variables mark 1 and mark 2 are always equal. Given that mark 1 and mark 2 hold the value of both sides outside and inside the loop respectively, they are only always equal if both sides is a loop invariant. Due to the shared dependency of loop unswitching and data code elimination on this semantic constraint, the two optimizations will behave in a coordinated manner, which can be used for cross-validation. Specifically, if data code elimination removes the if statement, if loop unswitching should move the if condition outside the loop, and vice versa. It's worth mentioning that The program on the right is mutated from the left for enabling the cross-validation between loop-on switching and dead code elimination. Overall, for a given program and target optimization, SBC selects an auxiliary optimization and, when necessary, mutates the given program into a variant for cross-validating the two optimizations. Then we compile the program and examine whether the actual behavior of the target and auxiliary optimization are coordinated as expected. If they are not, at least one of the optimizations misbehaves. Assuming the soundness of compiler, this misbehavior would only occur if an optimization is applicable but was missed by compilers. To realize SBC, two main challenges have to be overcome. The first is to identify optimizations that exhibit coordinated behavior and therefore suitable for cross-validation. The second is to derive the concrete coordinated behavior among optimizations against which their actual behavior can be validated. To overcome the first challenge, we propose a novel categorization of some common, well-known compiler optimizations, specifically optimizations that are applied due to related semantic constraints of input programs can be grouped together. In particular, we focus on two types of semantic constraints, invariant code and loop data dependency. The former refers to variables, expressions, and statements that evaluate to the same value under certain conditions. Loop data dependency, which occur when loop iterations access the same memory location with at least one write and are critical to loop-level optimization, such as loop vectorization. Optimizations that depend on the same semantic constraint can be cross-validated. Regarding the second challenge, we formulate two kinds of relationships among optimizations, co-occurring and complementary, each of which induce a specific type of coordinated behavior. In the co-occurring relationship, two optimizations are enabled by the same semantic constraint simultaneously. The co-occurring relationship means if one of the two optimizations is applied, indicating that the semantic constraint holds, then the other optimization should also be applied. The complementary relationship refers to optimizations enabled by semantic constraints that are negations of each other. That is, for one program, there is one and only one of the two optimizations that will be applied. If neither is applied, one is a misoptimization. For the optimization related to invariant code, we create a co-occurring relationship between them through code mutation. From the perspective of loop data dependency, loop vectorization and memory optimization via register allocation naturally exhibit a complementary relationship. We only need to constrain the input program to guarantee that one of the two optimizations can definitely trigger in the input program. For this example, if k is not a negative number, only loop vectorization should be applied. Otherwise, the data dependency contains a true dependency. That's memory optimization via register allocation can be applied. This means regardless of the value of k, whenever neither optimization is applied, one of them is missed. We evaluate SBC on two statements on two state-of-the-art industry compilers, LLVM and GCC, and consider every optimization mentioned before. We use Zhang to generate the test case. Based on our evaluation results, we reported 101 issues to LLVM and GCC, out of which 84 have been confirmed and 31 has been fixed. We evaluated the diversity of these missed optimizations and found that they are related to many compiler components, such as backend, value range analysis, and vectorization. To evaluate the real-world relevance of the found missed optimizations, we use code clone detection to look for evidence. Among the reported issues, we found some exactly clones of our reduced test code in real-world software. In addition, we evaluate the performance and compile time impact of these missed optimizations. The results show that such real-world code not only consistently improves the runtime performance, but also reduces compile time after these compiler defects are fixed. There are two key reasons for this result. Firstly, many fixes address the engineering aspects of the compiler implementation, rather than altering the underlying analysis algorithm. Secondly, many of the missed optimizations occur early in the optimization pipeline. When applied, they can reduce the overall compile time. In conclusion, we propose a new method for finding missed compiler optimizations. That's all for the talk. Thank you.
Thank you for the talk. We have time for one question, probably.
So thank you for the great work. So I'm wondering, like for those, so you use the Zhang for generating the test program and finding the missed optimizations. I wonder why didn't you? And you also mentioned that you have real-world clones of those like detect bugs. I wonder why did you not directly use the real-world code to find such like missed optimizations, which seems to be more realistic, and developers may be more willing to fix such bugs.
When we originally do this work, we wanted to generate more the program contains more optimization opportunities, so we can more effective to so we chose the random generator to conclude to do it.
Okay. Thank you.
We have just one short question, and then we have to move on. And the rest will have to wait.
Yeah, given things are like low overhead of the analysis, the computer optimization, I think it is technically impossible to integrate everything to the some runtime condition, just JIT. So that's where my concern. Is there any technical constriction or limitation on that?
Sorry.
Yeah. So you totally based on the traditional or typical static compiler like GCC or LLVM. So I wonder, is it possible to apply this methodology into the JIT?
Right. It can be used for other compilers.
Yeah. Okay. Sure.
Okay, thank you.
Thank you. You can take it to the coffee break within 15 minutes.